So based on that information, how would we figure out how much time it takes, if that's what we're looking for? How would time and force and final speed and mass relate together? First of all, if we're applying a force as time passes, what are we really doing to the object? What do we call a force applied for some period of time?
Momentum.
Momentum is closely related. The object has momentum. We're trying to give it a certain momentum. But force times time has the same units of momentum, it turns out. But what do we call a force for some amount of time? This is actually what we call the idea of impulse. Impulse is force times time. If you're applying a force to an object as time passes, you're exerting an impulse on it. The impulse is just the amount of force you're applying multiplied by how much time the force lasts, or the amount of time we care about anyway. In this case, the train is exerting 20 newtons of force, so that's force in this equation. And we don't know how much time. We want to figure out how much time it takes to achieve some results. And we can use the idea that impulse also equals the change in momentum. We usually abbreviate this as J for impulse. J equals F times delta T, so the impulse equals the force times the amount of time. And the idea is that the total impulse, the sum of all the impulses acting on the object, equals the change in momentum of the object. The total impulse equals the change in momentum of the object. So if we can find, in this case, I guess there's only one impulse. The train is exerting a force on the car for some unknown amount of time. And so the total impulse will just be the impulse of the train. So that'll be force applied by the train times the amount of time it lasts. So force from the train times some unknown amount of time equals the change in momentum of the car. Any questions on that so far? And we know the force from the train. We don't know the amount of time. That's what we're trying to find. How would we find the change in momentum for the car? How do we usually calculate momentum?
Mass times velocity.
Yeah, momentum is defined as mass times velocity. Or P equals M times V. So we can replace delta P car with change in mass times velocity of the car. Also, the mass of the car is presumably not changing, so we can factor that out of the delta. And just say change in momentum is mass times change in velocity. And that's going to just be final minus initial. And do we know anything about the initial and final speeds?
Initial is at rest, right? So it would be 0.
Yeah, so V initial is 0 and V final is
40 meters per second.
Yeah, so we know both of those values. We know the mass of the car. We also know the force of the train. The only unknown left would be time. So how would you isolate delta T in this equation? What would you need to do algebraically to isolate the time?
You would divide F train by mass times change in velocity.
Yeah, or other way around. The mass times change in velocity divided by force of the train.
Yeah.
So we now have a formula for the amount of time it takes. Mass times change in velocity divided by force of the train. And the reason it's set up like that ultimately, other than just the algebra, is that the more massive the car is, the more time it's going to take. The more you want to change the speed, the more time it's going to take. And the stronger the train's force is, the less time it's going to take, because it's going to be able to push harder. So we get delta T equals, if we plug those in, mass, 1,000 kilograms, change in speed would be 40 meters per second minus 0. So just 40 meters per second, divided by the force of the train, 20 newtons. And 40 over 20 reduces to 2, so 2 times 1,000 would be 2,000. And what would the units be there?
Seconds.
Yeah, because newtons is kilogram meters per second squared. So everything can, and in the numerator, we've got kilogram meters per second. So everything cancels out except for seconds. So it'll take 2,000 seconds for it to reach the speed that's desired. Any questions on that so far? And if this seems like an absurdly long amount of time, that's because 20 newtons is an absurdly small amount of force for a train to exert. 20 newtons is like the force it takes to maybe hold up an apple in your hand. A train I would expect to exert way more force than 20 newtons. So it should take a lot less than 2,000 seconds. It's just that the numbers in the problem are unrealistic in the first place. Any other questions on that so far? All right, then let's take a look at part 2 as well. So same car, 1,000 kilograms, but in a completely different scenario. We're now talking about a traffic collision between the 1,000 kilogram car and this 4,000 kilogram truck. And let's draw out the initial and final situations. In the initial situation, we have, we've got this car. Make that a little bigger. This car traveling north. I'll call this D for DeLorean. And a truck traveling west. So we'll call that T for truck. So the DeLorean and the truck. The DeLorean is traveling north, and we know its speed. And the truck is traveling west, and we know its speed as well. So if we just label those, we've got speeds of 30 meters per second to the north and 10 meters per second to the west. So that's what our initial situation looks like. Any questions on the setup there so far? And then what's going to happen to these as they travel?
They are going to collide.
Mm-hmm. And what happens, or what are we assuming happens to them after the collision? Do we know anything about after the collision?
Yeah, it seems like they stick together.
Do they say it stick together?
No, but when it says after the collision, the DeLorean is going west at so it's going the same direction as the truck.
Well, the same direction as the truck was originally going, but it doesn't tell us anything about what the truck's doing afterwards.
Oh, I see.
So we shouldn't make any assumptions about the truck's motion yet. We definitely know that the DeLorean, the truck, we don't know. So let's just mark the truck as unknown. So truck is going in some direction, but we don't know how fast it's going or what direction it's going at all. Maybe it even came to a complete stop. We don't know. But I wouldn't assume that they're stuck together unless it specifically says so. But we can at least draw in the final velocity vector for the DeLorean. This car is now traveling at, is known to be traveling at 30 meters per second to the west. And then the truck's velocity, we don't know. Presumably that's what we're actually trying to find out. We want to know how fast is the truck going and in what direction after the collision. Any questions on the initial and final situations so far? Then let's fill in what we can. To make the momentum chart, how do we calculate momentum, like the initial momentum of the DeLorean?
10 times the mass of the DeLorean.
Yeah, or it's going at 30 meters per second. So we multiply 30 times the mass. So 30 meters per second times 1,000 kilograms would be 30,000 kilogram meters per second. We want to specify direction though. If we're going, in fact, everything here is going to be kilogram meters per second. So instead of writing kilogram meters per second every time, I'm just going to put a little note at the top saying everything here is in kilogram meters per second. So 30,000 in which direction? Yeah, or I would say north, because it's not like the car is flying at the moment. It's just moving north along the ground.
Oh.
So 30,000 to the north. And we want to be able to write that in a more useful way. We want to write this 30,000 to the north in coordinates. So how would you say 30,000 to the north in terms of XY components? How far is that going in the X direction? If we treat north-south as the Y direction and east-west as the X direction, how much east-west motion does the DeLorean have at the beginning? Is it traveling east-west at all?
No.
So its XY component, or its X component then would be 0. And then since it's traveling with 30,000 momentum to the north, we would treat 30,000 as its Y component. So this would be the vector listed in component form, 0, 30,000, in the sense that it's got 0 motion to the east and west and 30,000 kilogram meters per second of momentum directly to the north. And this is a much more useful way of writing it than, I mean, writing it as 30,000 to the north tells you a lot of information about what's going on. But writing it in components, 0, 30,000, is much more useful for doing calculations with it. Any questions on that so far? And what about the truck? What would be the initial momentum of the truck itself?
Uh, 10 times 40, 4,000.
Yeah, 10 times 4,000 gives us 40,000, and that'll be to the west. So 40,000 to the west. And how would we write that as XY components?
It'll be 40,000, 0.
Yeah, 40,000, 0. Although since it's to the west instead of to the east, what would we usually call that?
Negative 40,000.
Yeah, we're going to treat to the west as the negative direction here. And that's not really mandatory. That's just the usual convention. The important thing is that you choose, for any dimension, you choose one direction along that axis to call positive, and then the other direction along that axis to call negative, and stick with that. You want to be consistent about it throughout the problem. By convention, we usually call north positive and east positive. Then south would be negative and west would be negative. Again, not mandatory, just the usual convention. So if we want to find the total momentum, how do we add these vectors together?
Pythagorean Theorem.
To find the magnitude, yeah. But in general, how do you add vectors?
I think for the total, you can just add literally the x components together and the y components?
Yeah, this is really the entire purpose of putting the vectors in component form in the first place. If they were like, if it was listed as just 30,000 and 40,000, you couldn't just add 30,000 plus 40,000 because they're not in the same direction. But by listing it in components, you can really just add the x component plus x component to get the new x component, and y component plus y component to get the new y component. So 0 plus negative 40,000 is negative 40,000. Just going to write this as negative 40K for now. And then 30,000 plus 0 would be positive 30,000. So those would be the xy components of the total momentum vector. And we could even draw that out as well. We've got these directions. We know it's 40,000 in the negative y direction plus 30,000 in the positive, sorry, 40,000 in the negative x direction, that is to the west, plus 30,000 in the positive y direction to the north. So the actual momentum vector is going to be this diagonal. And note that this is exactly what you get if you just add these vectors head to tail. If you just put these vectors together, like treating one of them as starting where the other one finishes, there's the total momentum vector. We are literally just adding these vectors together geometrically. It's just that using the component form allows us to do that with numbers as well. So there's our total momentum of the system. Any questions on that so far? And during this collision, what should we assume about the change in total momentum?
It's 0.
Yeah, this should be 0. And we're going to describe that as a 0 vector. 0 with a vector sign on top. This just signifies it's not just the number 0, it is a vector whose magnitude is 0. And how would you write the 0 vector as xy components?
0, 0.
Yeah, 0, 0. And note that this is not the same as just the number 0. The number 0 is just 0 and that's it. The 0 vector is a vector whose components are all zeros. And we usually just write it as the numeral 0 with a vector sign on top. So how do we use that to find the final momentum? Or what should we assume about the final momentum here?
Final minus initial will give us 0.
Yeah. In other words, the final momentum is
the initial plus the delta P.
Yeah, final is initial plus delta. In fact, that's a very useful way of thinking of a delta anything. Delta is just the thing you add to the initial value to get the final value. And if the change is 0, what does that tell you about initial and final values?
They're the same.
Right. If delta P is 0, then initial momentum is the same as final momentum. So the individual momenta are certainly changing, but we know that the total initial momentum and total final momentum are the same. And that's generally going to be true in any closed system. You know that how do we know that the change is 0 here? Why are we assuming 0 total change?
Because it's we're saying that it's conserved.
Saying that it's what?
Conserved.
Yeah, we're assuming momentum is conserved specifically because these objects are presumably only interacting with each other. If there were other forces involved from elsewhere, like the car and the truck are exerting forces on each other during the collision. So the individual objects change their momentum. But the total momentum is only going to change if there's another force from elsewhere, if there's an external force acting on the objects in the system. Maybe there's a strong wind, or maybe there's a third car involved that we didn't notice. But if there's no external forces, or if there are external forces but they all cancel out, then the total change would be 0. Which means the final result is going to be exactly the same as the initial result. Just another exact copy of that same momentum. So I'm just going to copy that directly over to here. which means that the final momentums of the car and the truck have to add up to negative 40,000, 30,000. But note that that alone does not tell us how it splits up. It could be any combination of vectors that add up to this value. So you're going to need to know at least one more piece of information. In this case, what is our one more piece of information about the final situation? What do we know about the final motion of the objects?
We know the final position of the DeLorean.
Yeah, we know everything we need to know about the DeLorean in the end. We know it's moving 30 meters per second to the west. So we can calculate its final momentum. P final for the DeLorean is going to be mass times velocity, so 30 meters per second to the west times 1,000 kilograms. So that'll still be 30,000 kilogram meters per second, but 30,000 to the west instead of to the north. So 30,000 to the west. And how would we write that as components?
Is it negative 30,000, 0?
Yeah, negative 30,000, 0. And so now the only unknown left is the final momentum of the truck. We've got to have values that make these add up to the correct total, negative 40,000, 30,000. So now we just need to fill in, and again, we can look at each component individually. The X components have to add up and the Y components have to add up separately. So looking at just the X components, we've got negative 30,000 plus something equals negative 40,000. What would that something have to be?
It would have to be negative 10,000, 30,000.
Yeah, because negative 30,000 plus negative 10,000 equals negative 40,000. And 0 plus 30,000 adds up to 30,000. So that means the truck's final momentum has to be 10,000 to the west and 30,000 to the north. So let's draw that in. We've got 10,000 to the west, so a little bit to the west. And then 30,000 to the north. In fact, we could even draw that into scale. It's got to be the same amount as the DeLorean's initial momentum. So 10,000 to the west, 30,000 to the north. And then we can just draw in an arrow that's going in that direction. North and west. Mostly north, a little bit west. So sort of north, northwest-ish. Any questions on that so far? And we could even put those together and see that these add up. If we take this DeLorean final momentum plus truck final momentum, those should add up to total final momentum. Looks pretty close. And of course, these drawings are not exactly to scale, but it's a good idea to draw them at least pretty close to scale to get a good visual idea of what's going on. Any other questions on that chart so far? And then as one final step here, we could also fill in the delta momentum. So how would we calculate delta for all of these?
Just final minus initial.
Yeah, final minus initial. So for instance, for the DeLorean, and again, we could look at this in terms of each component individually. Final minus initial for X, we got negative 30,000 minus 0, so that's negative 30,000. And then for the Y components, 0 minus 30,000 is negative 30,000. Same thing for the truck. Negative 10,000 minus 40,000 would be positive 30,000. 30,000 minus 0 would be positive 30,000. And what do those changes add up to?
0.
Yeah, negative 30,000, negative 30,000 plus positive 30,000, positive 30,000 adds up to 0, 0, the 0 vector that we should be expecting here. So this column, the delta column is often useful for one final check to make sure all the numbers fit together. Also, if we draw in those vectors, each one of those is going to have XY components. So 30,000 to the west, 30,000 to the south. And then this one, 30,000 to the east, 30,000 to the north. So those are going to look like to the southwest and to the northeast. Exact opposite vectors. Any questions on the algebra or geometry there so far? And we also want to label the magnitude and direction of each one of these vectors. So let's give that a try with a couple of them just to get some practice on that. If we are looking at, for example, let's take a look at change in momentum of the truck. Looking at this one specifically for the moment. We want to know, first of all, to find the magnitude. If we know that these sides are 30,000 to the west, 30,000 to the east, and 30,000 to the north, how do we figure out the magnitude, this diagonal here? Anytime you've got a right triangle, if you know the two legs, how do you find that hypotenuse?
The Pythagorean theorem.
Yeah, we can use a Pythagorean theorem. The magnitude squared equals the x component squared plus the y component squared. Hypotenuse squared equals leg squared plus leg squared. So the magnitude is going to be the square root of x squared plus y squared. We have those values, so we could just fill those in. Square root of 30,000 squared plus 30,000 squared. And usually we just plug those into a calculator, but in this case, we can use the special value, the special case that the x and y components are the same. So we could just say that's 2 times 30,000 squared. And then we could split that up. Square root of 2 times, and then square root of 30,000 squared, the squared and square root just cancel out. So in this case, the magnitude is just going to be square root of 2 times 30,000. Square root of 2 is about 1.4-ish, and that's going to work out to, may as well get a reasonably accurate number, about 42,426. And of course, that will be kilogram meters per second. So that's our magnitude here. Any questions on that so far? And we also want to label the direction. For direction, we typically use the angle that the vector makes with the positive x-axis. So we're looking for this angle here. And how could you find that angle? If you know both legs of the right triangle, the opposite leg and the adjacent leg, what trigonometric function would tie those together with the angle?
Tangent.
Yeah, tangent of the angle is going to be opposite over adjacent, so that'll be the y component over the x component. And then how do you undo tangent?
The inverse tan.
Right, we can just take the inverse tangent or arctangent of both sides. So the inverse tangent of the y component over the x component, since y is the opposite side from that angle and x is the adjacent side, and that should give you the angle. In this particular case, what do you notice about the x and y components? What's going to happen when we divide those?
going to equal 1.
Yeah, 30,000 over 30,000 is 1. And inverse tangent of 1, what's an angle whose tangent is exactly 1? What does that angle look like?
60 degrees.
What was that?
Isn't it 60 or like the multiples of it? Wait, actually it's
1. If the sides are exactly the same, yeah?
45.
oh,
Yeah. In any right triangle if the sides are the same, you know it's isosceles. And if one of the angles is right angle, the other angles have to be the same and add up to 90. So that's got to be 45. So generally, you would take the inverse tangent of this ratio of sides. In the specific situation where the side lengths are identical, that's got to be 45 degrees. So we could label that angle as the 45-degree direction. Makes that a little smaller. So we now know everything we need to know about this vector. We've labeled it in terms of its components and in terms of its magnitude and direction. So generally, it's a good idea to do that for all of these vectors. You don't necessarily need the information for every time, but it's a good habit to get into. Usually the X, Y components are going to be easier for almost any calculation you want to do. So generally, if you have vectors in terms of magnitude and direction, and you want to do any calculations with them, I would start by putting them all into magnitude and direction XY component format. Convert everything to XY components, do all the calculations you need to do, and then at the very end, convert everything back into magnitude and direction. Because magnitude and direction, like how fast is it going, which direction is it traveling, that's usually the information you actually want. But it's a nightmare to try and do calculations with those directly. The calculations become significantly easier when they're in magnitude or XY component format. Any other questions on that so far? So let's try applying this to one more. Specifically, let's look at the final state of the truck, because I'm guessing that that's really what we care about. We're trying to figure out what's the final velocity of the truck. So let's take this negative 10,000, 30,000 and convert that into magnitude and direction. So first of all, magnitude, we can still use Pythagorean Theorem, square root of x squared plus y squared, except now it's going to be 10,000 for the x component and 30,000 for the y component. Do I need to worry about the negative on the 10,000?
No.
Because
it's going to be squared.
Yeah, the fact that I'm squaring it anyway, even if I do fill in the negative, squaring it gets rid of that negative anyway. So in the Pythagorean theorem, you can just ignore negatives entirely. So we're going to get square root of 10,000 squared plus 30,000 squared. We can just treat kilo as a unit here. So 10 squared would be 100. 30 squared would be 900. And those would both be in units of 1,000 squared or million. 100 plus 900 would be 1,000. So 1,000 squared, in other words, a billion. But when we take the square root, we can split that up. Square root of 1,000 times square root of k squared, 1,000 squared. And on the 1,000 squared, then the square root, those are just going to cancel out. So we just get square root of 1,000 times 1,000. Square root of 1,000, I'll have to check on that. 31.6. So 31.623-ish times 1,000. In other words, 31,623. So that would be the magnitude here. This the truck's final momentum is 31,623 kilogram meters per second in this certain direction. Any questions on that magnitude so far? And we also want to find the direction. And there are a couple of ways we could do this. One of those ways, if we wanted to find, by default, we draw the direction relative to the positive x-axis. So positive x-axis, and then we're looking for this angle. What would you expect about the value of that angle without even doing any calculations? How big would you expect that angle to be? Or what are some limits on it? It's got to be bigger than what and smaller than what else?
90 and smaller than 180. Sorry, 90, yeah.
It's got to be more than 90, right? Because 90 would be from x-axis to y-axis.
Okay, so I meant bigger than 90 and smaller than 90.
Oh yeah, 90 is smaller than that angle. So the angle's got to be larger than 90. It's an obtuse angle. But even if we've drawn this wildly inaccurately, we know this angle has to be smaller than what maximum?
180.
Yeah, just from the fact that it's in this quadrant, the fact that it's going kind of north-ish, west-ish, the angle is going to be somewhere between 90 and 180. Those would be the extremes. So I would recommend at least picking that out, putting some limits on it before you even run any calculations. Just based on the way it's drawn, ask yourself which quadrant it's in. Is it between 0 and 90, or between 90 and 180, or between 180 and 270, or between 270 and 360? So which quadrant of the unit circle it's in, so you have an idea what sort of result to expect. The other one, this 45-degree angle here in the center, that was in the first quadrant. It was to the northeast. So we knew right away it was going to be between 0 and 90. In this case, though, if we try actually running the exact same calculation, just inverse tangent of y over x, y in this case is 30,000. X is negative 10,000. If you divide those, 30,000 over negative 10,000 would just be negative 3. And if we take the inverse tangent of negative 3, so inverse tangents, negative 3, I'm getting about negative 72 degrees. And that's a problem because we are expecting the angle to be between 0 and 90. Negative 72 is definitely not between 0 and 90. In fact, if you actually draw negative 72, negative 72 is since we define positive angle as measured counterclockwise from the x-axis, negative 72 would be the other direction, clockwise. So that would be our negative 72. Does that look like the direction that we're supposed to be going in?
No, it's the opposite direction.
Yeah, this looks like the exact opposite, or pretty close to the exact opposite. The reason for that is the inverse tangent function. If we took 30,000 over negative 10,000, we get negative 3. But if we had reversed that, if we had taken negative 30,000 over positive 10,000, so if we had gone 10,000 to the east and 30,000 to the south, the ratio would still be negative 3. The inverse tangent function cannot distinguish between northeast and southwest, or northwest and southeast. So the inverse tangent function is only going to give you values, in this case, you could say to the right of the y-axis, the first quadrant and fourth quadrant. Or to put it in angle terms, the inverse tangent only gives outputs between negative 90 degrees and positive 90 degrees. If the result you need is something other than that, like in this case, we knew from the start that it's going to be between 90 and 180, we've got to flip that around a full half revolution. And how do you change an angle by exactly half a rotation? Mathematically, what would you have to do to that negative 72 to swing it around exactly half a rotation?
Add 180.
Yeah, add 180 degrees to it. 72 plus 180 would be 108. So that means the angle we actually want is 108 degrees. So the angle we're talking about is 108 degrees counterclockwise from the positive x-axis. From taking the negative 72 degrees we got from the inverse tangent, noticing that that's in exactly the wrong direction, or exactly the opposite of the direction we need, so we add 180 to it. Any questions on the geometry there so far? All right, let me tidy that up. And so this would be the way we would describe the final momentum of the truck. (108 degrees counterclockwise from the east axis with a magnitude of 31,623 kilogram meters per second. Alternatively, you could say that the angle between west and the direction is 72 degrees. If you labeled this smaller angle as 72 degrees, you could say it's traveling in a direction of 72 degrees west of north. So mathematically, we would usually say 108 degrees from standard position. In terms of giving directions, you would usually say 72 degrees west of north. We also, let's say we wanted to find how fast it's going. We've got the momentum of the truck at the end. How do you convert momentum into velocity?
It's momentum divided by mass.
Divided by, what was that?
Mass.
Yeah, if we just divide that by the mass, that should give us the velocity. We can use momentum equals mass times velocity. Therefore, the velocity is just momentum divided by mass. Ignoring the direction for the moment, if we just take the magnitude, so 31,623 kilogram meters per second, and divide that by the mass, which was 4,000 kilograms, what happens to the units of measurement there? If you got kilogram meters per second and you're dividing by kilograms, what's left?
Meters per second.
Yeah, the kilograms cancel out. We're left with meters per second. And numerically, it looks like that works out to about 7.9 meters per second. So that would be the final speed. The truck, in the end, the truck is traveling at 7.9 meters per second. And in which direction? What can we assume about the direction of the velocity vector? If you're just taking a vector, the momentum vector, and dividing by mass, what happens to a vector if you divide it by a scalar? If you multiply or divide by a scalar, what should we assume about the direction?
Stays the same.
Yeah, the direction stays the same. So the velocity of the truck, the final velocity of the truck is 7.9 meters per second in the 108 degree direction. Same direction as the momentum, just in this velocity, the speed of 7.9 meters per second. So if we wanted to draw that out, we would just draw in this direction 7.9 meters per second. The final velocity of the truck, 7.9 meters per second at an angle of 108 degrees with the positive x-axis, or 72 degrees north of west. Any other questions on that?